Hello. So in this first section we're going to look at a couple of important problems that helped build the calculus called the tangent and velocity problems. Now the tangent, if you probably remember that term maybe from a trigonometry class, but we're actually going to use the concept of a tangent that you saw in geometry. So maybe it was a way back, but you might have seen a circle and you learned that you could draw lines to the circle, certain kinds of lines. And so if we drew a line that went through at 2 points on the circle, that was called a secant line. But if we drew a line that just touched the circle at 1 point, I'm going to try and show that here. Maybe it looked like that. This is a tangent line. It only hits the circle at 1 point on that circle. And it was called a tangent line. And so if we're talking about a more generic curve, some function f of x, we can use a similar terminology. We can draw a secant line to the curve, and it will go through 2 points on the curve. So let's say, for example, we have this curve f of x, and here's a, and here's b on the x-axis. Then I have some point here on the curve, and this point right here is a comma f of a. And then I have some point b, f of b on the curve. And then I can draw the line through those points on the curve. And this would be a secant line through those 2 points on the curve. All right, so a secant line is a line through 2 points on a curve. And then a tangent line, just like a tangent line for a circle, a tangent line is going to be a line that just touches the curve at 1 point. And so maybe at this point b f of b, if I were to draw a tangent line to the curve, it might look something like that. There is possibly a tangent line to the curve at a point. So a tangent line is a line that touches the curve at 1 point. And one of the early problems in the development of the calculus was figuring out how to find this tangent line. The problem was well known in geometry for a circle. It's relatively easy to find a tangent line to a circle, but for a general curve, it ended up being a difficult problem. And so what we figured out, well, not we, what mathematicians at the time figured out to do was, well, what if we took this secant line, and what if we let this b value, what if we took this second point and moved it closer and closer and closer to a? What if we took this b value and let it get closer and closer and closer to a, and take the subsequent secant lines, right? So we had our original secant line. What if we took this new secant line, and then what if we again let the b value get closer? What if we found that third secant line and we let the b value get closer and closer and closer? What happens? So we're going to explore this problem with a simple case, and then it's going to lead us to a process, and we're going to learn about that process, and that's going to lead us to eventually a general idea of how we can answer this problem about the tangent line. All right, so let's see an example. Let's get a concrete example in our heads. Let's consider the function x squared. Simple, right? Basic quadratic function. Let's find the slope of the secant line over each interval. All right, so if you remember back from beginning algebra or somewhere, the slope of a secant line, well, the slope is not a difficult concept anymore. We know that the slope is a change in y over a change in x, a rise over a run. And so we can think of it, if we go back to what we had earlier, we can think of the slope of the secant line to be y2 minus y1, to be f of b minus f of a over b minus a, rise over run. So let's keep that in mind. Slope is equal to f of b minus f of a over b minus a. So let's do that for these for a few of these exercises. So let's look over the interval from 2 to 4. All right, so from 2 to 4, then the slope would be f of 4 minus f of 2 over 4 minus 2, which would then be now f of 4. The function is x squared, so f of 4 would be 4 squared. That would be 16. F of 2 would be 2 squared. That's 4 over 4 minus 2. So that's, what, 12 over 2, which is 6. So if we look at that, if we consider the function x squared over 2 to 4, the slope is 6. The slope of that secant line. Let's get a visual of that. Let me bring up, I've got this set up in Desmos. And here, I've got this set up to where the function is x squared. And I've created a slider here. The a value is 2. That's in our sense, our starting point. And the h, that's the distance between a and the second point. So here I've got a is 2, b is 4. Here's that secant line in red. In black is the curve x squared. Here's that secant line. And the slope of the secant line is 6. Okay, so now let's change it. Let's bring that second point, let's bring that, instead of having the b value be 4, let's drag it closer and see what happens. So now, right, so in a sense what I'm saying is let the a value be 2 and the b value be 4 for the first case. Now let the a value be 2 and the b value equal 3. Alright, so now I have f of 3 minus f of 2 over 3 minus 2. Alright, so that would be 9 minus 4 over 3 minus 2. So that's 5 over 1, which is 5. Alright, so now if my b value is 3, if my second point is when x is 3, the slope of that secant line is 5. Let's verify this over on the graph. Let me drag this h to 1. Alright, because that's the distance. And so I've got the secant line going through 2, 4, and 3, 9. The slope of the secant line is 5. All right, so now let's see what we have. 2 to 2.1. Okay, now things, I'm getting closer and closer to 2. Right? So I'm leaving the a alone and I'm changing the second value. Now it's at 2.1. Right? So then this would be f of 2.1 minus f of 2 over 2.1 minus 2. All right, so f of 2.1, 2.1 squared, I think that's 4.41 minus 4 over 2.1 minus 2. So that would be 0.41 over 0.1, which is 4.1. Again, let's take a look at this on the grapher, on the Desmos. All right, so let me drag this h value down to 0.1. So notice these 2 points are getting closer and closer together, and now we see the slope of the secant line in red is 4.1. All right, and so we continue this process. Now over over the interval from 2 to 2.01. I'd have f of 2.01 minus f of 2 over 2.01 minus 2. I can't do this one in my head. F of 2.01, let's bring up a calculator. 2.01, if I square that, that's 4.0401. So I've got 4.0401 minus 4 over 2.01 minus 2. So that's 0.0401 over 0.01. That's 4.01. I think I can still do this on the Desmos. Let me drag my h value down to 0.0, oh, went too far, 0.01. See, now these 2 points are almost indistinguishable, and I see that the slope of the secant line is 4.01. Let me zoom in a little bit here. Oh. Right, they're almost indistinguishable, but if you zoom in, you can see that they're still a little bit apart. And now let's do this last one. From 2 to 2, if my interval is from 2 to 2.001, then that would be f of 2.001 minus f of 2 over 2.001 minus 2. I can't do this one in my head either. Let's see, 2.001 squared is 4.004001. We do the subtractions, so that's going to give us 4.001. I'm sorry. Subtracting 4 from that. 0.004001. 0.004001 over 0.001, and that ends up being 4.001. Now that was a long process here, but let's look at the trend. Let's see what's happening. Notice that my intervals, I started at 2 to 4, then 2 to 3, 2 to 2.1, 2 to 2.201, 2 to 2.001. This interval is getting closer and closer. I'm taking the b value and I'm getting it closer and closer to the a value. I'm keeping the a value steady, and I'm taking the b value and getting it closer and closer to the a value. And what's happening to these slopes? If we look at these values, they appear to be getting closer and closer to what value? Hopefully, you're thinking, hey, they're getting closer and closer to 4. Right? So these slopes, these values, right, if we look at these values, these appear to be getting closer and closer to 4. All right, now, what if we went on the other side? What if we said, instead of looking from 2 and then to the right, what if we instead said, well, let's look from the left. Let's look at numbers left of 2 and bring them closer and closer to 2. So in a sense, let's look at the other direction. Now, I'm going to show a process here. I'm going to change things up a little bit. I'm going to use the calculator because all this arithmetic's getting a little bit difficult. So what I want you to notice is, notice that in all of these expressions, we had the f of 4, or we had the f of the b, f of b, that was changing, minus the f of a wasn't changing in that case. And so now if we look at this one, now the f of b isn't going to change. So then I'd have, what, f of 2 minus f of 0 over 2 minus 0. Here this would be f of 2 minus f of 1 over 2 minus 1. Notice that that's not changing, the f of 2, and the 2 isn't changing. F of 2 minus f of 1.9 over 2 minus 1.9. F of 2 minus f of 1.99 over 2 minus 1.99, and f of 2, minus f of 1.999 over 2 minus 1.999. So notice in this case, the second terms are changing. So what I'm going to do is, in the calculator, to speed up this process a little bit so I don't have to do all this arithmetic, is I'm going to create a function. The function is, let's see, what's the f of 2 isn't changing. We know the f of 2 is 4. So in the numerator, I'll have a 4 minus, and then I'm squaring an input, right? My function was x squared. 4 minus x squared in the numerator. And then in the denominator, it's 2 minus an input, 2 minus x. And now I'm going to go to my table settings. Second, and the window button brings up my table settings. And I want to have my independent line over here on ask. So move over and toggle it to ask if it wasn't there already. Now let's take a look at the table. I'm going to delete some other stuff here. So now I just need to type in the other inputs. 0, right? If x is 0, then the slope is 2. If x is 1, then the slope is 3. If x is 1.9, the slope is 3.9. 1.99, 1.999. So we get these slopes 2, 3, 3.9, 3.99, 3.999. And if you don't want to set up the thing on the calculator for that, that's fine. You can just go through the arithmetic one by one. It works the same. Now, again, notice what's happening here. Let's look at these values. What's happening to these values? They again appear to be approaching 4. Right? As my interval around 2 gets smaller and smaller, these outputs for this slope formula get closer and closer to 4. Let's take a look at this situation now over in Desmos. Let me zoom back out. So now what we're doing is saying we still have the a equal to 2, but now my starting point, my h, was 2 to the left, and so it was at 0, 0. And so notice that the slope of the secant line is 2. That matches what we got numerically. And then as we drag this h value to 1, look what happens to the slope. And there's that red secant line. Now the slope of the secant line was 3. And as we continue to drag, look at what's happening in green to the slope of the secant line. What's happening there? As the distance between the points gets closer and closer to 0, the slope of the secant line appears to be getting closer and closer to 4. Okay. So, it appears, from what we've seen so far, it appears that the slope of the tangent line might be 4. Alright, so what we found is the slope of the tangent line appears to be 4. Right? We looked at those secant lines, but we let the interval around 2 get smaller and smaller and smaller, and we found that the slope of that secant line got closer and closer to 4. So it looks like the slope of the tangent line is probably 4. Alright, so draw the line through 2, 4 with the resulting slope found in the previous exercise. So here I've got the graph of x squared, and here's the point 2, 4. There's the point 2, 4, and a line with slope 4. All right, so you know how to do this from algebra. let's see, if its slope is 4, go up 2, 3, 4, right 1. Or from that original point, I can go down 2, 3, 4, and left 1. And so if I try and draw this line, drawing lines is never easy with the tool that I have. If I try and draw this line, let's see if I can so there's a line, poorly drawn, that appears to hit the curve at 2, 4, but just at that point, 2, 4. This is a tangent line. So it appears that the tangent line hits curve, right? Hits the curve y equals x squared at the point 2, 4 with slope 4. Now it's just coincidence that those 4's are the same. That's just coincidence. And we can write the equation of that line. You learned how to do that back in algebra classes. Use a point slope form. You could write y minus y1, right? Y minus y1 is m by x minus x1. So y minus 4 is 4 by x minus 2. And if we take this over to a slope-intercept form, it's y equals, what, 4x minus 4. And so there's a tangent line to the curve at x equals 2. Now, of course, the difficulty is, well, what if we didn't want the tangent line at x equals 2? What if we wanted the tangent line at x equals 3? Now we've got to go through this whole process again. There's better ways to do this, but we've got to build towards that. We can't start, we can't start with just the answers. That's no fun. You've got to build the process and understand what's happening in the background so you understand, especially when your answers might not be right. All right, so what we're going to do is we're going to learn more about this process and then build a general understanding of how we could answer this problem in a much, much quicker way. But that's off in the future. All right, so let's see another example. So here we've got, let g of x be the square root of 2x plus 1 and p be the point where x equals 4. And we're asked to determine the slope of the secant line, PQ, where Q is given by these various values, right? So if Q equals, is where x equals 3.5, then Q is where x equals 3.9, etc., etc. All right, so let's see. So P is 4, and Q is 3.5. All right, so in a sense, what we're doing first, if x is 3.5 and then x is 4, we're really finding, let's look at the interval from 3.5 to 4. All right, so then the slope would be g of 4 minus g of 3.5 over 4 minus 3.5. Now, we're going to have some square roots in here. This is going to be a mess. But what I know is the 4 is always going to be constant in these problems, and the other thing is going to change. All right, so then the next one's going to be 3.9 to 4. And so then I'd have g of 4 minus g of 3.9 over 4 minus 3.9. Again, this is going to be kind of messy. But I can again do this on the calculator as long as I know some understanding of what's going on here. So let's see what's happening. Let's go back to our y equals screen. Let's clear out that old stuff. G of 4, that's not changing in these problems. So g of 4 is the square root of 2 times 4 plus 1. 2 times 4 is 8. 8 plus 1 is 9. The square root of 9 is 3. So in the numerator, I have a 3 minus, the square root of the function. So now let's input the function, the square root of 2x plus 1. Leave the square root, close it off. And then I've got to divide that by, in the denominator, I'm going to have 4 minus my input. Close that off. So here's the function I'm going to use. That's my slope function for this problem. And now let's go to my table. It's still in the ask setting. Let's delete the old stuff. And let's type in, my first input is 3.5. And then my second input is 3.9. And then my third input is 3.99. 3.999. Let me drag this over here. So let's take a look at these values. What's happening, right, as my inputs, you know, we're keeping the 4 steady, and as my inputs get closer and closer to 4, what appears to be happening to the outputs? All right, what's happening here with the outputs? I've got 0.34315, then 0.33521, then 0.33352, then 0.33335. What appears to be happening here? Looks like these are getting close to 0.3 repeating, which is 1/3. All right, well, let's look at it from the other side. Let's change up. So now let's go back to our calculator, and now let's clear out the old stuff. And now we're going on the other side. What if we had 4.001? Oops, not. And 4.01, and 4.1, and 4.5. So now, again, let's take a look at these values. What's happening to these values, these outputs, as my input is getting closer and closer to 4? I've got 0.32456, 0.3315, 0.33315, 0.33331. What's happening with those outputs? Again, they appear to be getting closer and closer to 0.3 repeating, or 1/3. So, from this, it appears that the slope of the tangent line to g of x, when x equals 4, it appears that the slope of the tangent line appears to be, we'll see, approximately 1/3. Okay, now write the equation of the tangent line. All right, well, the equation of the tangent line, now that we know the slope, well, the point, when x was 4, the output was 3, wasn't it? Right? F of 4, 2 times 4, g of 4. 2 times 4 is 8, 8 plus 1 is 9, the square root of 9 is 3. So we had the point 4, comma 3, and we had the slope 1/3. So we could write y minus 3 is 1/3 by x minus 4. Or if we wanted to write this in a slope-intercept form, y equals 1/3 x minus 4/3 plus 9 9/3, right? Because 3 is 9/3, so that would be plus 5/3, I think. All right, and again, if you don't like this whole calculator issue, the way I've done this with the calculator, then you can do these manually, right? Using a calculator, just using what you've learned on the calculator in the past. You'll get the same results. I'm just making the process a little bit quicker by building a new function. All right, so now the topic was the tangent and velocity problems. So we talked about the tangent. What does the velocity have to do with this? So here, let s of t be a position function. S of t is negative 16t squared plus 90, and let it represent the position in feet of a rock dropped from a height of 90 feet, and the position is after t seconds. Now we're asked to estimate the velocity of the rock after 1 second. The velocity. All right, well, velocity. How are we going to figure out a velocity? Well, here's one thing I know. I know that if we had back in algebra, if we had a consistent rate of speed, then we had a basic distance formula. We know that distance is rate times time. Right? Rate, that's the speed, the velocity, right? So if I manipulate this a little bit, just divide through appropriately, then r is distance over time. So now let's manipulate this just a little bit more and say, well, then this is what we knew if we had a constant velocity. However, let's instead change this a little bit. So then instead of a constant, what we're going to say now is, well, then the average velocity over a time interval is going to be the change in position, right? A distance. A distance is a change in position, isn't it? Over a change in time. An average velocity is a change in position over a change in time. So if we want the velocity of the rock after 1 second, here's what I'm going to say. Well, let's find the average velocity. Let's find the average velocity over the interval 1 to 1.5. Let's find that average velocity. All right, so then that would be the change in position. All right, so the position function is the negative 16 t squared plus 90. So then I'd have the position function at 1.5 minus the position function at 1. The change in time would be 1.5 minus 1. Hey, doesn't that look familiar? Isn't that exactly what we were doing in the previous exercise? We just had a function, a different kind of function. We were looking at the slope of a secant line. Now this is just an average velocity. And then if we wanted to, we could make that interval smaller. Let's go from 1 to 1.1. And so then I'd have s of 1.1 minus s of 1 over 1.1 minus 1. So let me show a different way to do this on the calculator. If you didn't like the other way I was doing this, let's go to our y equals screen, and let's, instead of inputting this fancy function I'm creating, let's just input the function that was given. Negative 16x squared plus 90. Got to use x on this calculator instead of t. Now, let's go back to the home screen, and let's create an expression. All right, so if you weren't aware of it, now from that y equals screen, I can use this y variable. It's called y1. So if I go to the home screen, now let's input this function. Let's put in parentheses for the numerator. I want y1, so go to the variables, go to the y variables, hit enter for function, and there's the y1. y1 of 1.5. Close that off. Subtract. Now I need y1 of 1. Variables, y variables, function, y1 of 1. Close off the numerator. I need to divide that by the quantity 1.5 minus 1. Close that off and hit enter. Negative 40. Now, well, the nice thing though is since I typed that all in one line, if you hit second and the enter button, it brings up that last line of code that you typed in. Hit second and enter, and it brings up that last line. Now I just need to make some adjustments. I need to change, let's see, what do I need to change? I need to change that 1.5. Every time I saw 1.5, that needs to be a 1.1. Don't forget to change it in the denominator. And hit enter. Negative 33.6. All right, so what do we have so far? This is negative 40. This is negative 33.6. All right, now let's make the interval smaller. Let's find the average velocity over the interval 1 to 1.01. Well, again, that would be s of 1.01 minus s of 1 over 1.01 minus 1. Bring up the last line of code. Quick way to move all the way to the left. Hit second and the left button. Moves all the way to the left. Let's see, I need to insert a 0 here. So put your cursor over that 1 after the decimal point. Hit second insert. Type 0. Okay, let's move to the right and do the same thing in the denominator. Second insert a 0. All right. The rest is fine. Hit enter again. Negative 32.16. All right, now let's find the average velocity over 1 to 1.001 seconds. Second enter. Insert another 0. Move to the right and do the same thing over here. Negative 32.016. What's happening here? What's happening to these values? All right, well, maybe that's not enough evidence. Let's find another one. Let's do one more. Let's insert, let's hit second enter again. Let's insert 0. Let's make it 1.0001 in both the numerator and denominator. Negative 32.0016. All right, so the average velocity over the interval 1 to 1.0001 is negative 32.0016, right? I think. What's happening here? It appears, what's happening to the average velocity? The average velocity, right, over these smaller and smaller intervals, the average velocity appears to be approaching negative 32. What would the units be on that? Let's see. The units on the numerator, those were positions, right? So a change in position. The position was in feet. The units in the denominator, 1.5 minus 1, those were change in time. Those were in seconds. So feet per second. Now, of course, we can also do this in the other direction. What if we kept the, what if we, instead of starting at 1 and thinking from the right and getting closer to the 1, what if we kept the 1, then started from the left and got closer to 1? Let's verify this. Let's make sure that it's reasonable. All right, so now let's find the average velocity on the interval 0.5 to 1 and then how about 0.9 to 1, and then the average velocity from 0.99 to 1, 0.999 to 1. Let's see if that gives us similar evidence. All right. And it turns out, if you remember how slope works, the order in the numerator and denominator doesn't matter as long as you're consistent. All right, so let's bring up that last line of code. And instead of doing 1.0001, how about let's just do 0.5 in the numerator and in the denominator. All right, so negative 24. And second enter. Let's change those 0.5s to 0.9s. Negative 30.4. Let's change those 0.9s to 0.99s. Negative 31.84. And let's do one more. Change them to 0.999s. Negative 31.984. All right, so what appears to be happening here? Again, we're centering, we're getting closer and closer. Right? My interval is near 1, and it's a very small interval near 1. And the average velocity is, again, getting close to 32 feet per second. So, my conclusion, estimate the velocity of the rock after 1 second. My estimate of the velocity, I would estimate that to be negative 32 feet per second. Again, now notice something really important is it was the same problem. This average velocity problem was the same problem as the secant problem, right, to the tangent. Finding an instantaneous velocity, we can find an average velocity over a small interval. Finding a tangent line, we find the slope of the secant line over a small interval. Both of these problems were based on the same process, called a limiting process. And we're going to talk more about limiting processes for the rest of this unit, and we're going to learn ways that we can approach them and evaluate them without having to use necessarily tables and calculators. There are other ways that we can evaluate them. But we've got to learn about the notation and how to approach them before we can come back to this problem and say, hey, there's a better way to do this. There's a more general way that we can find these slopes of tangent lines and velocities. So that's where we're going for this first unit. All right. Hopefully you watched the whole thing. Have a great day.